It's my great pleasure to introduce my colleague, Jacob Collard. We have been working together for a long time. Currently, he leads a project on language and standards. Uh, He's a computational linguist in the Software and Systems Division of the Information Technology Lab at NIST. His research focuses on representation of natural language semantics and pragmatics, including methods for automatic grammar induction and natural language query systems. He received his PhD in linguistics from Cornell in 2020, where he studied formal grammar induction. Afterwards, he joined NIST to study language in applied concepts, including material science, computer security, and research mathematics. Over the past 3 years, he has led a project to develop language processing tools for standards. These tools have been used to identify potential inconsistencies, retrieve information, and track dependencies in standards related to surface metrology, digital twins, semiconductors, and forensics. He was awarded the ITL Building the Future Award to advance this research. With that, I will hand it over to Jacob. And I just want to make a remark before he starts. That is, if you start thinking about how you design, you will see language is at the heart of it. And language and discussions and discourse is at the heart of it. With that, I'll hand it over to Jacob.
Yeah, thank you very much, Sub. Today I wanted to talk about design as discourse, which Sub kind of alluded to, is that a lot of what we do is really at sub level very dependent on language, whether it's our day-to-day communications or a collaborative engineering work. We're using language every day, and so we should understand enough about that language to leverage all of that data that we're creating. We're kind of constantly creating data via communication, and this applies to a lot of engineering design work, and these documents come together if you're building requirements, if you're defining standards, if you're defining interfaces, etc. These all come together and interrelate to each other via their linguistic structure. So I'm going to skip over some of this. This is adapted from an earlier presentation, but these slides are really just showing if you have a lot of standards, if you have a lot of documents that are coming together to build out your work, those are at least in part expressed using language, and that natural language is informal, but it is expressing something that often can be very complex and mathematical or physical, and thus kind of connects to something that is more formal. The functional properties of an object that you're defining, the code or the schemas that you're using, the characteristics of physical entities and their geometries. And all of this comes together, expressed not in a nice, simple mathematical expression, but in a complex jumble of different documents that are describing all of these things. And these descriptions require maintenance as the standards change or as other documents change. We need to be able to understand what those changes imply and what they mean for the rest of the work. And so this trail, this network even of textual documents, information, and all of the knowledge that's contained in these things is critical to understanding our engineering processes, in particular our systems engineering processes, and our other collaborative works. In particular, this work has focused on standards, in what you might think of as smart standards, which we are thinking of as standards that have some sort of formal structures alongside or in place of the natural language, which you can think of as the informal. So we need to formalize critical parts because that gives us the ability to verify things, but we also need the flexibility of language because this is a collaborative work. And we need to get all of these ideas together, and then we need to relate them to the physical world. And language is really one of our best ways of doing that in a flexible way. So we could think of standards development as a discourse in two ways, actually. One is as we develop the standard, we engage in a discourse among the standards developers to say, well, what do we want to add? How do we want to define this term? But the end product is actually also part of a discourse. When we put forth a requirements document or put forth a standard, we are communicating still, and we are presenting new content to new interlocutors. In this case, we are presenting it to the users of the standard, but we still need to think about what action is that trying to communicate? What are we trying to do with that standard? And when we do so, how does the context that envelops that whole system change? That's kind of some background about standards, and I want to get a little bit into the linguistics to talk about how can we possibly really do anything with language. It's a very complex system. We use it every day, but we don't necessarily understand very well how it works or how we could possibly communicate with this thing. And often miscommunications arise. And then I'll get into what can we practically do computationally to analyze the language that we're using, bridge the gap between informal language and formal structures, and that's going to allow us to perform queries and check for consistency in our documents in a way that is at least verifiable at some level. And of course, there's ambiguity, but we can create something that looks formal, even though it's created through this informal system. So we know we produce massive amounts of data. In particular, we're talking about standards. There were over 1,000 standards produced just by ISO in 2023. Of course, that is just one out of many standards development organizations, and that's just 1 year. So there's really, and then of course there's books, articles. We're producing tons and tons of data, linguistic data. So if you think about as an individual needing to understand all of this linguistic data, to say you're writing a new manufacturing standard and you've joined the committee, there's 8,000 current manufacturing standards in ISO alone. So how are you supposed to be able to understand all of that content? Maybe over the course of your career, you'll read all 8,000, but you're not going to read all 8,000 in a short period of time. And these are long documents. And so there's this huge barrier to entry. And it's honestly in particular domains, for example, artificial intelligence that are growing really fast, all of these quick developing emerging technologies related in particular to information technology are growing so fast that there's just really no way, it is not humanly possible to actually keep up with this linguistic data that we're creating. To make things sort of more difficult, the computational tools that we have access to right now are really quite limited as well. We're storing language in documents, which is fine, but it's a little bit, it's kind of what we've been doing for thousands of years. We've adapted it a little bit to the computational era, to the information era, but we haven't really changed the overall structure very much. Now we're storing things as PDFs a lot of the time, but a PDF is really not that far off from paper. It's quite difficult for a machine to process the information in a PDF. And when it does, it is still not really aware very much of the structure of that document. And it's still fixed into a single presentation. And if you're thinking about standards, we really want standards to be presentable in a variety of different ways. To be able to say, hey, I want to look at the requirements of this standard. I don't care about anything else. And often, because these documents are interrelated, I don't want things just out of one document. I want things out of many different related documents. So this discrete document-based structure, I think, is becoming a little bit outdated, because it's really just one step up from paper. And if we can go beyond, have better search tools, have better analysis tools, then we can really start to access the information that is in language, and not just think about characters in sequences. Um, I mentioned the complex structure of standards. This is actually just showing the internal structure of a single standard. This is the structure of definitions in that standard and what concepts are being used to define other concepts or terms. So this is coming from a engineering lifecycle management standard. So we have concepts like process and activity, and all of these are being used to define each other in a complex web. And so we can see that there are particular clusters of concepts that depend on each other. There are certain concepts that are more important for defining other concepts. And then there are other clusters that are maybe less complex, but that doesn't necessarily mean that they're less important. But the key point here is just that there is a lot of complexity in these documents. And we don't necessarily see that when we just see it as a list of definitions. And that was just looking at a single document. But if we look at multiple documents, we of course get further complexity. This is looking at some surface metrology standards and how they interrelate. The idea here was, this is, again, terms being used to define other terms. And each cluster of nodes in this graph represents a single document. So we have information flowing from one document to another, between certain documents and not between others. So we have this vertical flow from the blue to the pink to the yellow on the left, but not so on the right. But we have the horizontal flow from the blue on the left to the blue on the right. And some of this is intentional. This is how the standards were structured, with the idea being that the information should flow in a certain way. But if we actually look at the information, most of the information flows that way, but some of it actually does not. So you may be drawn, for example, to this circle over here. There is one circular definition in this family of documents, one term that is just defined in terms of itself. So there's really no way to understand what it actually means. And then it's not really possible to see just looking at the graph, but there is a cycle of information that flows from the blue in the top left through the little triangle to the top, bottom right, and then to the bottom left, and then back up. That we have circularities that arise due to the complexity of this system. And that is also, again, it produces a definition that you can't really fully understand unless you already kind of know what the terminology means. And even then, you're not getting an exact, precise definition. Standards also just depend on each other. You can include requirements by reference to other standards, or you can so you have these normative references between standards. This is just part of the dependency graph for a single standard. I started with one standard, ISO 14253-6, and I tried to find all of the different standards that you would need to understand in order to understand that one singular standard. And this gets really complicated. It's referencing not just different standards, it's referencing specific versions of those standards. And sometimes if you follow the whole path, you're referencing different versions of the same standard. So we have, for example, the 1998 version of ISO 14253-1, but we also have the 2002 version of that standard. And you have to reference both of them. You have to access both of them according to what is actually presented in the standards. So, and then some of these standards are no longer released. They're outdated. And so the problem is that these structures are not made explicit in the representation of the standards. We still have this flat document structure, and these links are present. They're hyperlinks now in some cases, so you can click on the link and go to the ISO website, but the structure that results out of that is not made explicit, and so we can't analyze these graphs without doing some manual work to extract them and see that there is some chaos going on in the structure. And this isn't even about language necessarily, but these references are embedded in the language as well. And so without understanding what these references are trying to do linguistically, we have even less understanding of what the structure is. We have all of this chaos, all of this complexity, and the goal is we want to be able to access and reason about the linguistic data that is collaboratively constructed in, for example, design processes or standards. So we want to take all this information and reason about it. But right now, all we can really do is perform string-based searches on it. It's quite limited. So we need to understand the semantics of our documents. We need to be able to interpret the propositions that they make. So for example, we need to understand the requirements and understand exactly what those requirements are trying to say and whether they conflict with each other, what they depend on. We need to understand the definitions that they are proposing. And again, so definitions are actually a pretty easy case. We can identify things that we want in definitions and things that we don't want. So for example, circularity is, you're always going to get circularity in a full lexicon of a language, but if you're just looking at a single standard, the goal is to not produce any circularity so that you can have some semblance of consistency. But all of this is really about understanding the propositions that we make and how they fit together. So we want to be able to take a requirement such as this one here. The application shall allow users to create a new document from a chosen document, etc., and represent that in some way that we can reason about, because the computer can't really reason about this text. You could put it into an AI, and I'll talk a little bit about the relation to AI here in the sense of large language models. But what we really want is to be able to do some fairly concrete, formalized reasoning here so that we can verify things. And artificial intelligence can be great for first pass runs, for summarization, things like that. But when it comes to verification, large language models are not verifiable. And so for something like standards, which are intended to be as verifiable as possible to really be measurable, that doesn't really seem to fit in with the goals. So this leads us into then pragmatics. We also have to represent not just what the propositions are, but how they fit together and how they form a common ground. Who is contributing to them? What time and what context are they appearing in, so that we can reason about them appropriately? Because if we just reason about everything, assuming it's all in the same context, then we lose access to that information, and that's going to affect what those propositions really are meaning. So I've proposed this sort of structure of interpretation of language. This follows more or less from the model that linguists use to process language. We start with this sort of underlying signal. In the case of speech, it's the acoustic signal that we produce. In the case of text, it's a visual signal. In the case of assigned language, it's also a visual signal. In the case of a computer, it's a signal, electrical signal, and so on. But that electrical signal is interpreted into some sort of categories, which we might call phonemes or morphemes, which are then organized into syntactic structures, which are then organized again into, at a higher level, into pragmatic structures. Notably, there's no semantics on this list. I don't really make that much of a distinction between syntax and semantics. There's a mathematical reason for that that I won't really go into, but suffice it to say that when you have a good enough syntax, you should have access to most of what we might think of as the semantics. Because yeah, I mean, that's what the syntax is there for, is to give you access to the semantics. So I'm gonna skip through a good portion of this, but the basic idea is, as we go up this level, as we go up this hierarchy, we are processing things into more formal structures. So we start with very informal things, such as symbols. This is from the Indus Valley script that has not been deciphered. And so we don't know what it means. And in fact, without the conventional understanding of this language, we don't even know what symbols are symbols. We don't know what are distinct symbols. So there's a bunch of different variations on a character, for example. This glyph that shows somebody who seems to be carrying something, but does it matter if they have feet depicted or not? Does it matter if they're carrying something round or something elongated? Until we understand the language, we don't know what the sort of categorification of these symbols is. So this is one hypothesis showing how these symbols may come together to form categories, but we don't know that this is true unless we understand the language. And so the idea here is that there is convention involved and that there is uncertainty involved. Even if you do understand the language, sometimes, for example, an English speaker will get confused about the difference between an A and a G. They look similar enough that sometimes we can't tell. There's noise. But there's an interesting property of language as we move up the level into the syntax. And that's that the goal may be to understand meaning, but there's a lot that we could do without understanding that much about the language. So this here is a text in Sumerian, and I'm actually going to skip ahead to here. We can actually do a lot of reasoning based off of the form without knowing what any individual word means, aside from maybe some like little function words. So this is the key to formal logic, essentially, is that we can reason about things. If I say every x is a y, and I say z is an x, then I can conclude, without knowing what a z or an x or a y is, that z is a y. And so even without knowing Sumerian, I can reason about these structures. And that's the idea between this syntax and semantics interface and the relationship between the two. Because if we understand the syntax well enough, we can do reasoning. And that's going to be really important because honestly, semantics is just really difficult. To really represent the meaning of a word or a phrase is not something that we're really very close to doing at this point. So one other point that I want to make, which is related to that, is there's been this hypothesis, the distributional hypothesis about word meaning, given by linguist John Rupert Firth, that says you shall know a word by the company it keeps. And I think this is a really important point that is often kind of misinterpreted, or it's not misinterpreted, but I think there's two interpretations that we need to keep in mind. So the idea is that if you had a really good statistical model, you can predict what word goes in a space based off of the words around it. And if you have that predictive function, then that could be how you represent the word, is by the function that determines where it can appear in a text. So if you know how to use the word, then effectively you could say you know how it means, you know what it means. And this is really the core of how LLMs work. This is perhaps a little bit of an older model, back in 2002 or 2020, 2019 area, as opposed to our current transformer-based models. But a lot of the start of this sort of AI revolution came about from this idea of filling in spaces with words and representing the words based off of that. And that's really useful. It's really powerful because again, we have this. If we do that, we get access to sort of how you use the word. But what we don't get access to is any further interpretation. We don't get access to structure. We just get access to what words go where. So when I think of the distributional hypothesis, that is just a part of it. And we need to also think about their distribution structurally. It's not just about their position in a linear text. So this leads us into syntax, the construction of structures between words. And so this might be represented as a tree. This is a very standard way of doing it in linguistics, to say, well, two words are related in that they form a phrase together. And then you can form a phrase out of a phrase and another word, and so on, to construct complex phrases that have different features and have some sort of meaning. And the idea is that any phrase carries a distinct meaning, and that meaning is predictable based off of how it's put together. So, for example, I can construct a taxonomy based off of the syntactic structure of words. If I have a new document, I know that it's a document because syntactically it says that it is. I don't have to know what a document is. All I have to know is that new document has a modifier over document. And in so doing, it has made it more specific. Again, if I add new empty document, that also makes it more specific, and so on. Then we get into the pragmatics, which is where we want to be able to say there are relations not just between words and other words, but relations between words and the contexts in which they appear, and how we infer these relations. So we have utterances, but now we also have context, and that includes the interlocutors, the people making the utterances, and it includes the reference, the things that we're actually talking about. This has led into a philosophical linguistic form called speech act theory, which is about what we do with language. We don't just spout random things into the void. We speak with some sort of purpose, where we might make an assertion, which has the goal of updating our common ground, coming to some understanding about a particular proposition, and there's some plan, presumably, behind which propositions we choose to try to convince people of, to try to update to the common ground. And then we might direct people to do things. We need stuff to happen, tell people to fetch us the salt, to perform some action, to update the world based off of our language. And then we might seek information. And so these are very broadly classes of actions that we might take using language. But the idea is that it's not just about spouting things into the void. It's really about collaboration. It's about how all of these utterances that everybody in a community is producing come together. And we can think of the complexity of standards or of requirements documents or of whatever other collaborative work as a bunch of utterances that are coming together into what should be a common ground. And whenever we speak to each other normally, we can choose to reject things. We can decide, hey, that is not yet something that I'm willing to accept into our common ground. I don't believe that. Here's why. Let's continue to debate that concept or that assertion that you've made. In a standard, it's a little bit more difficult to do that once the standard is published. But it's actually something that we really want to do as we're developing the standard. We want to be able to understand this common ground isn't quite as common as we think it is. There is some sort of error here. And we can do that by thinking of each utterance as an utterance, of each element of the standard as an utterance. So for example, we should be able to think about updating the system, updating the set of propositions that we have made in a standard with a new element. And when we do that, when we perform this operation, this speech act, essentially, we should be able to verify that it fits into the resulting common ground. And there is a whole formal theory of how this might work linguistically, that basically you have different representations of those different speech acts. And when you perform those speech acts, you have different operations that you perform. So when you perform an assertion, you're updating the common ground. And there's a quite formal definition of how you might do that. And we can apply those same techniques, not just in this abstract ivory tower linguistics way, but in actually a very practical way where we can check whether our standard is consistent.
This seems to have similar intent as sysmel,
Pardon, what did you say?
No, I was saying, is the intent here very similar to the sysmel kind of approach?
Not well. The idea is that standards are negotiated between people. The definitions, the precision, because language becomes very, very important. I've been in one standards committee where the fight was over whether a parameter was discrete or infinite. It has consequences in actual practice in the way you use it. So it's really about getting at the core of the definitions. Jacob, you're back?
I'm back. Sorry about that.
Yeah.
Lost power
Anyway,
for a moment.
I'll answer that question. Go ahead, Jacob.
Okay. So I'll just finish up here, just a little bit further to go, as I bring this into the how do we apply this to standards part of the talk. What can we actually do with this linguistic theory, and where can we go with this? So the basic idea presents this architecture here, where we want to be able to take standards documents or whatever documents that we have, requirements documents, and process them in some way to put them into a representation, in this case in a database representation, and then perform queries over that system that give us useful information out of it. That information may be error detection, finding inconsistencies or potential errors, potential fallacies in the text, managing dependencies, the interrelationships between information, and retrieving knowledge, retrieving the relevant content for me, for my use case. And all of these are related to each other. Really, they're all kinds of knowledge retrieval in a sense, but they're retrieving different kinds of knowledge. And understanding those dependencies is really critical, for example, to understanding the errors that we get. So the technology for this really exists, more or less. We have the ability to process syntactic structures, we have the ability to construct database representations, and we have the ability to perform queries over that based off of the linguistic understanding of those syntactic structures. And we can connect that also to the document structures or whatever other metadata that we have available. And so we can start to actually do this. This graph here is a graph of the dependency structures in a computer security standard. And so we can query for this dependency management type question. And in this case, at the center, we start seeing these key foundational concepts, and at the periphery, we see less foundational ones. So at the center, we have things like system and security, these very bare bones building blocks of our concept system for computer security. At the periphery, we get things like organizations, which are crucial to the process of security, maybe, but they are not themselves defining any other concepts. And when we do so, we can identify things like circularity. We can pull out errors. So there were two definitions in this NIST risk management framework standard that are cyclical. We have, to oversimplify a little bit, we have a threat source is defined as something which triggers a vulnerability. And then we have a vulnerability, which is something that is triggered by a threat source. There's a little bit more to each of these definitions, but if we boil them down to just that part, we have a relation, but we don't really have a concept of what these terms actually mean, other than that they are the names of arguments in a relation. And so this definition could probably be written a little bit better to better identify what that is. And that was across two terms, but we can actually identify, because this is a relatively efficient database model, we can perform queries over lots and lots of data, and we can pull out cycles across many different definitions, say 9 definitions. And in this case, we have network and network control and security control. And so what happens in this case is that the problem was an overloading of the word control. We have network control being the the control of the flow of information in a network, and that is contrasted with security and privacy controls about ensuring that we have security and that we have privacy in our systems, which is, of course, the core meaning of control in the context of this security standard. But other kinds of control exist, like that network control. And so if we're not careful, we overload the use of the term, and it's not clear which one we actually mean in this case. And so by identifying this cycle, we can pull that out and say, we need to be careful. We need to specify that network control is different from what we're talking about when we say control in this case, in the bulk of this standard. We've also done some work on identifying structure in definitions. A lot of this, again, is focused on definitions because they're relatively easy. They're relatively structured already, but they could be more structured. We could pull out their linguistic content in useful ways. There is a standard on terminology work in standards, ISO 704, that lays out guidelines for defining terms. And that, by leveraging that structure that it gives us, we can, for example, create visualizations of concept systems, automatically break down our terminology into meaningful components, and test conformance to that standard. So we've applied this to digital twins, and the Digital Twin Consortium, among other entities, is considering how best to define the term digital twin. Well, we've looked at 70 different definitions of digital twin to see what are the common elements of them and what are the uncommon elements. So we can break them down into their linguistic components and cluster those components together, see which ones contrast or conflict and which ones are common. So we can break them down into, for example, their superordinates or their superclass, and see that there is a lot of commonality. A lot of things refer to digital twins as some sort of representation or model. Other things refer to them as assets. So we have different equivalence classes, different groups of concepts here based off of either their superordinate or their characteristics. And that allows us to reason about smaller bite-sized elements of the definitions rather than trying to wordsmith from the very beginning. I showed you this concept system earlier, that this can be automatically constructed based off of the linguistic structure and give us an idea of what are the relations between the terminology or between other structures. Moving beyond what we have now, the same principles can be applied across the board to any collaborative work. This is not limited to standards, but it could be applied to requirements, to issues or support areas, to scientific articles. And we want to develop measurements that really pull this into the quantifiable realm. Being able to identify how well does this standard conform, how many conflicts does this produce, do the requirements conflict with each other, and does a standard meet the requirements that it's trying to, the requirements of the problem that it's trying to solve. And then there's also some work with LLMs that these two systems can be combined into hybrids in a variety of different ways to really leverage both the versatility of LLMs and the formality of formal linguistics to bring you something that is verifiable, but also easily understood and robust. And then there's many more applications. There's a lot of additional work to do verifying the inferences that we can make. Those structural inferences are sort of fundamental. And we understand inference in logic, but inference in language is a little bit more complex. There's ambiguity, there's context dependence, and there's a lot more going on. Language is not exactly a logical system, but we're coming to better understand it, and in so doing, we can better reason about what the results are, identifying new kinds of conflicts, identifying new kinds of new ways that we can show that a common ground is really being built when we're working with standards. So better representation of context is key to that, as well as our understanding of how these speech acts interact, especially when we get into domain-specific areas and things like modality, how we express possibility, for example, or different realities, different possibilities. And then building useful user interfaces to this is, of course, going to become important in terms of actually applying this to real standards. But that is all that I have. So I'm happy to take questions. Thank you.
Thank you, Jacob. I will let others ask questions.
Okay, may I ask?
Sure.
Sir?
Sure, Sam. Yeah.
Thank you, Jacob, for a very thought-provoking talk. I have two questions, and let me ask one at a time. My first question is, what has been the role of linguistics, science in general, and pragmatics in particular, in developing the large language models?
That's an interesting question. So the role of linguistics in development of large language models, there hasn't been that much. There has been some linguistics applied to the benchmarking of large language models, how we evaluate them. So for example, there are natural language inference data sets with the goal of being able to test whether an LLM can perform this kind of syntactic or semantic reasoning over the language that it's processing. And that ultimately does descend from linguistic sciences, from semantics, from logic. But unfortunately, a lot of those benchmarks are really not ultimately grounded in linguistics. They are descended from it, but what they're actually testing is maybe something different. And this is done for computational reasons or practical reasons. So for example, a lot of the natural language inference, the goal is to be able to test whether a conclusion can be reached from a premise. But the way that those data sets are generated is often crowdsourcing based off of image data sets. So there's additional context which the annotators are aware of, but which are not present in the benchmark itself. So what we're testing in those cases is not necessarily what we actually want to be testing linguistically. Yeah, go ahead.
Oh, I'm going to complete here.
And I was just going to say a little bit more has sometimes been brought in. There's hybrid models that incorporate, for example, dependency structures, part of speech tagging. So there is definitely some linguistics in the overall model, but in terms of the benchmarking and really what's going on, there's been fairly limited linguistics involved.
Thank you. Sub, may I ask a second
Sure,
question?
sure, please. I work with him, so I don't need to ask
Okay,
questions.
all right. My second question or comment, I guess, is excellent analogy or parallel between languages, natural languages, and standards. I thought in natural language, the usefulness of our words and phrases and sentences arise from the imprecision of meaning. Because if you make the meaning of shirt precisely this object I have on my body, then what you're wearing, it will not be a shirt.
Right.
Same thing seems to be true for standards. Pursuit of precision taken far enough in language or standards becomes self-defeating. Usefulness of standards for, say, tables or chairs or light bulbs depends on their imprecision. It depends on the specification as well as the imprecision. So it
Yes.
seems to me that pursuit of precision that you seem to suggest at the outset uh, may not necessarily get us better and more useful standards. There's some kind of balance between
Yes.
precision and imprecision in its good standards,
Hmm.
and that's a very nice parallel with language, but somehow I missed that in your presentation.
Well, I said, I think at one point in the beginning, that part of the goal is to bridge the informal and the formal. And both have really useful properties. The formal is verifiable, the informal is not. But the informal is, as you say, very flexible. And it gains a lot from its imprecision. So it's definitely a balancing act, but I think what we can do is build a bridge that says where we are imprecise and where we are not. Verify what we can and connect it to what we cannot verify. So the overall model that I'm proposing here doesn't actually get rid of any of the information that is in language, including its imprecisions and ambiguities. It provides an interpretation, and that interpretation at some level, right? And so there is additional precision that is added on, but in some cases you may not want that precision because because of the ambiguity. But in a lot of cases you do. In these definitions, you can specify just enough. You specify what the key elements are, but you don't specify all the details of them. So I break the definitions down into components, into smaller elements, but those elements are still linguistic structures. So we've gone from completely informal to semi-formal, if you will. And in so doing, we've made certain things precise, but kept a lot of things. We've kept that flexibility of natural language where we need it.
Just to add a comment, Sham, the way we do the processing, he does the processing, is that every term is indexed back to the sentence in which it appeared. So we are not losing the context, the natural language context in which that term was used.
Mm-hmm.
And hence the precision itself can be revised depending upon how you reinterpret the natural language. So the natural language preserves the ambiguity, whereas the formal language, you can think of it as a tentative formalization which you are using, because often in standards what happens is when it is actually implemented, certain types of ambiguities are discovered, and that comes back and revises the standard in order to deal with, especially in material stuff. So you can see the dynamic between the practical application and how it is coming back and changing both the ambiguity and potentially even increasing ambiguity sometimes, because the textual part is not lost.
Thank you, Sab. If I may just make one more comment here,
Yeah.
that, you know, when I learned computer programming, long ago. I discovered that in formal language of computers, say Fortran, there are no real numbers.
Mm-hmm.
They are floating point numbers and they are
Right.
integers, but neither of them are real numbers.
Yeah.
Because there's no way to represent a real number from mathematics.
Mm-hmm.
But that's a thought that I think was raised by Sub's comment, but I'll stop here and let others.
Mm-hmm.
I
mean, in the formal system, there's going to be a limitation in any formal system. That's my position.
Yeah, absolutely. But we want to leverage the benefits of the formal system, and then when those limitations are reached, we still have our flexible informal systems.
Thank you.
Yeah, I have a couple of questions. One is, can you go to that slide on the ISO standards hierarchy?
This one?
Yeah, right. So if you take this picture, so for example, the first document is referencing some 2006. Then the next document has a reference to 2015. So would you consider this as a inconsistency that a document of 2006 has a reference to 2015?
Well, so the 2006 document has a reference to the latest version of the standard, which happens to be the 2015 version. So it is not necessarily an inconsistency. It's just that one has been updated more than the other. Now, that may have created an inconsistency because the 2006 document is not actually aware of the things that its referenced document has implemented because it wasn't written yet.
Yeah. So a related question is, how do you actually extract these relationships between the concepts in a document? Is it done automatically or manually?
So
The network
this
diagram which you have shown.
image, yeah, the network diagram I've shown here, this was created manually, but we're moving towards being able to do it automatically. The standards do include explicit references to each other, and that's what we're capturing here. But we just haven't implemented that yet to do it automatically, but it's possible.
However, the concept structures are extracted automatically. You may want to describe the parser.
Everything else is done automatically through the syntactic parsing.
Yeah. So a related question again is, why can't we take the annotation and a typical machine learning approach to this extraction, as opposed to looking at these concepts and mapping them?
You mean for which task in particular? For the concept mapping?
Yeah, for the concept mapping, like for example, to build this kind of map, why can't I rely on the current models of NLP or any of them, and with some manual annotation? Are we missing something, or what's the difficulty in taking that route?
Well, we can, and actually we do to a certain extent. So the parsers that I'm using are actually transformer models that are operating under the hood. But once that is applied, it's creating a structure rather than just giving the output directly. And so that structure that is created can serve multiple purposes rather than just one. So you could say to a machine learning model, generate the concept system for me, and that would be okay. Potentially, it would. It has a few problems. One is that, well, that concept system is is just the one concept system. And what I'm proposing here is linguistic analysis that can then feed into actually multiple concept systems or different queries to produce different types of output. And two, because of because the neural network model is a bit more of a black box, it's harder to change when something is not what you expect it to be or not what you want. It's a little bit more difficult to change that model than it would be to change the database model that of the linguistic structures that I'm operating with here.
Just
Okay.
to add one more thing. The other thing is when you use these machine learning models, you lose the indexing back to where it appeared in the language. You see, here we are tying everything. Yes, we are using the parser, and after the parser, every sentence has been converted into a graph structure which is stored in the database. So we are able to go back to the precise sentence. There is a continuity between from the formal to the informal, and there is no black box in that sense.
Okay. Okay. So one last question is because your concept information from a standards document would have some indications of functions and structures, right? So is it possible to actually extract the purely from a function perspective and start looking at all the structures which support a particular function?
That's one of the goals, yeah.
Okay.
So for example, the requirements extraction is a very useful task. You want to be able to look at, well, what are the actual requirements of this standard aside from just the informational content that it's providing for you. And so that's definitely something that we that's a very broad category, but a function, but it is something that we can extract.
And
Okay.
also remember the 4 clusters he showed you, they are divided into definitions, metrology, and uncertainty. There are various pieces which are there. So if I'm in the manufacturing part, I only want to know certain parts of the standard, not everything. So we will be able to deliver specific structures for that particular functional role in the organization, in the case of manufacturing, for example. And also another point I want to make, here we are not trying to automate everything. We are trying to facilitate the collaborative negotiation process between different people coming together to develop a standard. Remember, they are building a common good, common ground in terms of language. So it is more a helping process in order to find disparities in each other's definition so that they can come to an agreement. So we are not trying to automate, we are trying to expose things using automatic tools in such a way that this process will be easier than they do now. Because if you go to a standards meeting, you'll see paper shuffling all over the place. So that kind of wastage of time can be eliminated through this process. Any other question? Incidentally, it's not limited to standards. We have been asked a few times whether we can use it in law or even policy documents that are being generated.
Yeah. The other one I was thinking is the occupation standards, where we still have a lot of vagueness in terms of when you say mechanical engineer or electronics engineer. There are some national occupation standards, but there may be some kind of differences and overlaps in the way they are defined. So
medicine too.
Yeah.
Yeah. We've been looking a little bit at medicine, certainly.
Sure.
See, I think by inverting the problem to say we are using language and collaboratively coming to agreements of language that we use to accomplish our tasks makes it very generic at one level. At the same time, it works very well in structured environments like standard. That's why we started with Standards Plus. We are at NIST, so it provides a base, and standards are very good because it is effectively a collective task. Right? There is nothing you can escape from it. Doesn't
Okay.
look like.
Yeah. In that case, we can wrap it up, Sab.
Thank you, Jacob, for the talk. As I said, he's the one who leads this effort. I work with him, and it's been a great fun working with him on these topics. Thank you, Jacob.
Thank you, Jacob. Thank you so much.
Thank you
Thank
all.
you.